Okay, here's another question on gravitational potential. This one includes a graph, so we're going to have to do some reading off the axes to get some of the values. The question says, the graph below shows the gravitational potential energy, EP, of a 1 kilogram mass varies with distance r from the centre of Mars. The graph is plotted for positions above the centre of Mars. Now, one thing to note, this is actually the gravitational potential energy, although even though it's in joules or megajoules, you can think of it as the potential because it's for a 1 kilogram mass. Okay, and remember that the potential is the work done per mass, and if you want to know how much work the field would do, or maybe how much loss in gravitational potential energy, so it's potential energy at that point, it would be the mass times the change in that potential. So in other words, this graph is for the gravitational potential energy it has, but that's because it's for a 1 kilogram mass. So we do have the mass in this. Right, so first question. Explain why the values of EP are negative. So this is similar to the opening question from another exam style question we've done. But essentially, it's this idea that you are going from an infinite point out in space, far enough away from the planet that it has zero potential, and so you are, as you move towards the planet, you are losing energy. Okay, so it's this idea of having a negative potential the closer you get to the planet. So just for 2 marks then, zero potential at infinity. And then for that second mark, a number of ways of putting it. You could say about the energy inputted to move it from infinity, the work done by the field moving the object from infinity, or something like the potential energy falls as object moves from infinity. Okay, so you write out here at zero potential, and as you fall down, as you get closer to the Earth at a new potential, that should be a more negative value, because whatever gravitational potential energy was stored at that position, it has gone down. Right, B. Use data from the graph to determine the mass of Mars. Okay, so this is a key equation, and from that equation we can actually determine the mass of this planet if we know the potential at a specific distance from the center. So we are going to get these two values by reading off the graph. Just remember that we do have this value, it is just wrapped up as the potential per kilogram, the potential energy per kilogram. So what we need to do then is we need to read off two values, and then to find the mass we are just going to do VR over G. So when reading off a graph, it's easier to find a point on the line where the scale shows an easy point to reference, so you're not going in between squares. So for instance, something like this, that point's quite easy to see. Yeah, it meets the line there, and I can quite easily read off the scale here. Another point, there's a point, so we could read off that, and that would go off this line. Makes it a bit easier than picking a point, say here, where you're having to read off in between those squares. So, and then that would have been somewhere here, and it's in between squares. So you're guessing again, okay? So you're kind of making an estimate of what the value should be. Whereas here, it's quite clearly on the line, or as close to as it looks. Right, so which value should I pick then? So, and firstly we need to work out what the scale is between the values that are written. So this is 25, this is 30, and there's 5 in between, so it's going up in 1 times 10 to the 6 meters, so this would be 26. So r is 26 times 10 to the 6 meters. please note the scale. And then here, this is going from 0 to 2 in 5, so it's going up in 0.2, so that'd be 0.2, 4, 1, 2, 4, no it's not, it's going up in 4s, so that would be 4, 8, 12, 6, 1.6. Okay, so that's 1.6 megajoules, okay? Or we can take that to be the potential as megajoules per kilogram. Right, so let's put these values in. So I had a potential of minus 1.6 times 10 to the 6 joules per kilogram. The distance it was away was 26 times 10 to the 6 meters. I'm going to divide that by the gravitational constant, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. So when all those numbers are inputted into there, we get approximately 6.2 times 10 to the 23 kilograms. Okay, so the mass of Mars from these points give us 6.2 times 10 to the 23 kilograms. It all depends on where you read off your graph. You probably will get a range of values, and usually your mark scheme will say a range of values between whatever. But that's clearly going to give us a mark because we're within that range. All right. Next question. Okay, so this says calculate the escape velocity for an object on the surface of Mars. So the idea behind escape velocity is how fast you have to travel to have enough kinetic energy to actually get up to this zero potential. So what we need to work out then is just how much energy that is. Okay, so mass times that change in potential, which is from the surface to nothing. So it is essentially the size of the potential at the surface, and that's our gravitational potential energy, and that should equal the kinetic energy. So the masses cancel, and so if we want to work out the speed, that's going to be twice this change in potential, or twice the surface potential, and then find the square root. So we can do that directly by finding out the potential, or likewise, if you want to know the surface potential, you could just calculate that if you knew m and r. So going back to this graph, we can technically directly work that out, because we can find the potential at the surface, or we could just go ahead and use our value for the mass of the planet Mars, and for we need to know the radius of Mars, so you'd have to read off there. So two ways of doing that really: directly reading off the graph, or reading off how large Mars is in terms of its radius, and then you can read off its potential at the surface. How about, why don't we, well, we know from the last question, and then that would mean I'd need to read off the graph to get the radius. So what's this? If I carry that line up very roughly, it's halfway between 1, 2, 3 and 4, 3.5 times 10 to the 6. So I'm going to use that, 3.5 times 10 to the 6 meters. So I'm going to put that into here to get my potential at the surface, times it by 2 and get the square root. And it should give me how fast this needs to travel to gain enough kinetic energy to then transfer that kinetic energy into gravitational potential, which will take it up to the zero potential point where it can escape the pull of Mars. Right, so numbers. So the velocity equals 2 times 6.67, so g, times 10 to the minus 11, multiplied by the mass, 6.2 times 10 to the 23, divide that by 3.5 times 10 to the 6, and then take the square root of all of that. And if you do that, it comes out at 4,900 meters per second. Okay, so you have to be traveling 4,900 meters per second so that you have enough kinetic energy, like I said, to gain enough gravitational potential energy to escape the pull of the planet. And then finally it says show that the graph, okay, so show that this graph shows that the this gravitational potential energy is inversely proportional to the distance away from the center of the planet. So how would we do that then? Well, if you actually multiply values of EP and R together, you should get a constant value. And if you do keep getting a constant value, then clearly the gravitational potential energy is inversely proportional to the distance from the center of the planet. So we need to pick out some values, probably do this 3 times. We've already got one step from our original question part B. I've pulled out another one there, we could use that, and then also we could probably, well, it seems as though we know that that's 3.5 at the surface. That's pretty much roughly going to there, which would be 12.6, is that? 12.5, sorry, 4, 5, yeah, 12, no, it's going up with 4s. Yeah, 12.6, 12.6. So let's do that then. So the first time I said R was 26 times 10 to the 6 meters, and EP at that point was minus 1.6 megajoules per kilogram. Sorry, we'll just say it's the gravitational potential energy, so megajoules. So that's one value to do. Another value was 15 times 10 to the 6 meters away. At that point, the potential was 2.8. So gravitational potential energy, 2.8 megajoules. And then the final value we'll take at the surface of the planet, and that's minus 12.6. The negatives are just representing the fact that you have to put energy in, so it doesn't matter that there's a negative value. That just means putting energy in. So that's the loss of gravitational potential energy at that point in the field. So what was I saying? So we've got 3.5 times 10 to the 6 meters, and the energy at that point is 12.6 megajoules just megajoules. Right, so EP times R, so 26 times 10 to the 6 times 1.6 times 10 to the 6. What does that come out as? And EPR 2.8 times 10 to the 6 times 15 times 10 to the 6. And then finally, EPR 12.6 times 3.5 times 10 to the 6. Okay, so this then would come out at approximately, I haven't got a calculator, it's on my phone. Let me just type this out on the computer. .6 times 3.5. So that would come out as 4.4 times 10 to the 13 newtons per kilogram. And then if we've got 26 and 1.6, that comes out as 4.2 times 10 to the 13 newtons per kilogram. And then finally 2.8 times 15. That's 4.2 times 10 to the 13 newtons per kilogram. So I think that's consistently looking fairly similar. and so we can conclude from that that the gravitational potential energy is inversely proportional to the separation from the position of the mass to the centre of the planet. There we go.